Okay, cool. So hello, everyone. I'm Peter. This is my first year here as an assistant professor in computer science. I recognize a lot of y'all through collaboration talks and my machine learning classes. So yeah, thanks so much for coming. This is going to be a little bit of a new presentation for me. I'm going to pilot a lot of new material. So we'll see how it goes. It's going to be very unrehearsed, except for the beginning part, which is about my overall research theme, which is in general on digital phenotyping, which is the use of digital devices that we all already have to quantify human behavior and other aspects of our body, and to use that precise subjective quantification to deliver scalable, accessible healthcare to others. And so during my PhD, and I won't talk about this for too long because I think you all have seen this talk before, but I worked on autism, which is a condition that affects 1 in 40 children in the United States, and it's characterized by several behavioral characteristics such as lack of eye contact, trouble with social responsiveness, difficulty with emotion recognition, and many other behaviors. I'm kind of having a flashback because during my job talk, it was here and it was like these exact slides at the beginning. So this time it's hopefully low stakes. So autism is a spectrum, or at least people talk about it as a spectrum colloquially, where you hear people say that autism ranges from low to high severity in this 1D spectrum. That's actually a very misleading way of talking about autism. And in fact, there's been a lot of literature to show that autism actually consists of multiple behavioral spectrums, a spectrum of emotional sensitivity, a spectrum of motor skills, a spectrum of social communication, and many other independent spectrums. And what makes autism particularly difficult to study from a scientific standpoint is that you could have one child who is diagnosed with autism, who has a great degree of emotional sensitivity and very low motor skills. You can also have a child without autism who also has a great degree of emotional sensitivity and low motor skills. And then you can have another child with autism who has low emotional sensitivity and high motor skills. So for these reasons, it's what we call a heterogeneous phenotype. That's a fancy way of saying it varies a lot between people who have the same diagnosis. And because of this complication, there are several diagnostic bottlenecks to diagnosing autism. One of which is that there are really long questionnaires to diagnose the condition, but unfortunately, only a subset of those turn out to be required if you apply a data science method called featured selection, where you take as input the questions that are used to diagnose, and as output, you look at the outcome variable. You actually find that you really need a small subset of those questions to diagnose autism. But nevertheless, because of this long questionnaire, the waiting time for the current standard of care currently exceeds 18 months on average in the United States. And sadly, this results in systemic discrimination of underserved and marginalized populations who do not receive access to healthcare because they don't get diagnosed early enough. And with autism, the earlier the diagnosis occurs, the more effective the eventual therapy is. But digital phenotyping as a general paradigm can potentially help. If we can deliver healthcare to people who traditionally are left out of the system, who live 3 hours away from the closest healthcare provider, who can't get it paid for, or who can get access, but who need reinforcement beyond the weekly or bi-monthly visits that you typically get in psychiatry. Via the phone, we can provide potentially, or at least the hope is, to provide more care. So I want to walk through the digital phenotyping process that I used during my PhD, and then I want to talk about how this overall research paradigm is currently being expanded into a bunch of other projects in Hawaii, which is really exciting. And I'll highlight a lot of my students' projects. So the first step in digital phenotyping is to create digital interventions for health monitoring. These can be delivered on a phone, on a wearable, on a website, on no longer Google Glass, but back in the day, people thought Google Glass would be popular. And so we prototyped some things on Google Glass and ran studies on them, but then it didn't take off. And the hope is that, yes, it's collecting data, it's monitoring, but it's also providing an intervention. And maybe the intervention should be the primary reason that users are using it, but as a aside, it's collecting thorough data about the user, which can be quantified using machine learning, and the resulting AI models can be integrated back into these devices to provide an adaptive diagnostic and digital therapy. So not a therapy that one size fits all, that's provided to a child with autism and is doing the same thing for every child, but where the AI measures the progress of the child and adapts the therapy accordingly. So at least that's what I looked at in my PhD. But now I want to focus mostly today on what my current students are working on, which mostly falls within this overall digital phenotyping pipeline. And one of the big takeaways of my PhD, which was kind of mixed feelings, was that quantifying complex social human behavior is hard and currently beyond the scope of what AI can currently do, which is, on one hand, kind of disappointing because I was like, yeah, I'll go in 6 years, figure this out, but that didn't happen. But I think it's an exciting area for an entire career of making AI that can quantify human behavior, that can understand it, and maybe it won't happen, but I will be advancing AI in the meantime, and hopefully as we advance it, apply it to healthcare. And that requires a lot of methodological innovations in machine learning. So I want to start by talking about some of the machine learning projects, the hardcore data science projects that some of my students are working on. One of these areas is in multimodal machine learning as a method. So a lot of times you have a machine learning model with one input, but when we're quantifying the human body, we often want to measure multiple signals at once. So EEG, or with a Fitbit, there's like 5 signals: heart rate, ECG, accelerometer, gyroscope, many other signals. And they're sampled at different frequencies. They measure different parts of the body, but they're often correlated. So a lot of this work is around, okay, if we have all of these continuous signals from a person, how can we use them together to make diagnoses? And currently I have a student, Young, who is working on multimodal machine learning for affect recognition, so emotion recognition, looking at 2 data modalities, one from videos of people, so looking at their facial expressions, which is kind of a measure of people's outwards appearance, as well as their brain signals, so EEG, and which is more of a measure of what's going on internally. We're using a publicly available data set for now, and have built a multimodal model that incorporates both and predicts emotion using both modalities. And we're starting to look at, okay, if you take away one modality, how does that affect the performance? And you could essentially run ablation studies to see which modality is the most predictive. And so results are coming in, but so far what we found is that it works really well from a personalized perspective, where the training data comes from the person, and then the test data comes from that same person later on. And I'll talk about that a little bit more, but this idea of personalized machine learning, aka overfitting severely to that person, but in a good way, turns out to be the key, I think, to machine learning for these complex, otherwise unsolvable AI tasks. Another thing that I'm looking at is fair machine learning. So a lot of the data set used to train machine learning models is inherently unfair, is unbalanced across demographic groups. So you have 80% of the data coming from white populations and 20% from everyone else. And then as a result, when you train the model, the accuracy in F1 score and all these measures is much higher on white populations than others, just as an example. Whatever group is overrepresented in the training data, it tends to have better performance. So I'm starting to look at what are ways that we can improve that algorithmically, given that it's not always feasible to get data that's balanced from every population. How can we innovate algorithmically to make the AI more fair regardless? And we've been looking at a couple of ways of doing this. One way is through the optimization procedure itself. So for those taking machine learning, you know that we typically optimize the error. We want to minimize the error. That's usually what we want to do. And sometimes I talk about this a lot in class, sometimes we penalize having undesirable properties in a machine learning model, regularization, where that undesirable property is having too many model weights. That's the common thing. But there are other undesirable properties you can penalize when you're optimizing your model. And so in this case, there turn out to be quantitative definitions of fairness. And there's different quantitative definitions of fairness, but what we can do is penalize the model being unfair while we're optimizing it. So we're jointly minimizing the error. So we want where error is, how different is the true value from what's predicted. So we're trying to minimize that discrepancy. That's usually what you do, while simultaneously ensuring that the model performs equally across each group mathematically. So that's kind of a fun exploration.
These some type of metric that we use a distance.
Yeah, so this is a distance metric between two different groups. And this is one definition of fairness in this algorithmic fairness literature. Yeah, it depends. And so there's actually like 20 different fairness metrics, and they all mean different things. And what's interesting in this area of work is that there's usually this trade-off between fairness and accuracy or F1 score or whatever your metric you're using. But there's also a trade-off between different metrics of fairness. It's kind of, people haven't really explored this too thoroughly. So we're starting to look into this and see what we find. And so a lot of complicated ethical questions here too, like, okay, you're making it more fair, but then the overall accuracy is going down. So how do you balance that? And unsolved questions at this point, but really exciting nonetheless. And we're starting to look at this with John Shepard's data in JAPSOM in the Cancer Center, who has breast cancer data. And so we're, and from a diverse population, together with what's called the multi-ethnic cohort study, which largely overlaps with the breast imaging data. There's people in both. And so we're looking at actually potentially multimodal machine learning that's looking at data from dietary data from the multi-ethnic cohort study, but also breast imaging data, put those together. And first of all, that's just interesting to predict from both of those at the same time. But on top of that, make it fair because there's different groups. So combining this multimodal with the fair machine learning. Another approach to fair machine learning. So Armin is a student who's starting to work on this project, and he just started this semester. So really exciting to see where that goes. Another approach to solving lack of fairness in machine learning is in the data side. So we've talked about the optimization side of the model. How do you optimize the model so the output is the most similar to the true value, but you could also change the input of the model to artificially make it more balanced. And there's a few ways to do that. A naive way is just to repeat in the data set the underrepresented groups so that the number is the same as the other represented groups. Of course, when you do that, it's still kind of biased because there's less diversity within the upsampled group than there is in the other group. but it's a good starting place. Another way you could extend that is to apply data augmentation, which who knows about data augmentation from machine learning class? Okay, a few hands. And so basically data augmentation is a fancy way of saying if you have a data set, you want to increase the amount of data that you have so that it's more diverse and doesn't overfit to certain situations. You, for example, inject noise into the data, you repeat it by rotating an image, you repeat an image by zooming in, zooming out, and you take one image and essentially turn it into 30 images, essentially using Photoshop transformations. And that teaches the model to learn to generalize better. So instead of, a cat is always standing face up, well, if it's tilted this way, it's still a cat. If you add some noise to it, it's still a cat. So basically doing that for fairness, where when we're repeating these underrepresented data points coming from underrepresented groups, we apply these data augmentations. So it's not just naive repeating, but it's actually, you're still getting some diversity there. Actually, some of the preliminary data I found on this is that it actually still doesn't help too much when you apply these basic data augmentation strategies. So what we're now looking at, and I talked to one of my friends at another university, is looking at GANs, or like the deepfake technology, so that when you're upsampling, you actually create a deepfake like modifications. So usually when you hear about deepfake, it's like really negative, but in this case, deepfake for good. So we'll see how that goes. It's also kind of challenging to implement, so we'll see if that works, but something that we're looking into. So the third area is personalized machine learning. And I think this area is, the first two are necessary if we're going to build machine learning models for healthcare that work and are deployed in the real world. But a lot of these tasks we're trying to predict on are really complicated. And so, like, for example, emotion recognition or stress detection or things like that, where the state-of-the-art models are all like 60% in the mid-60s accuracy, F1 score, and there's so much work in that literature, yet how good they get is 65%. And part of the reason is these are really, really subjective tasks. Like, are you stressed or not? Super subjective. But it's probably not as subjective within a person. So building one model, so traditionally when people build machine learning models, they're trying to build one model and then apply that to everyone. That's kind of the traditional way of thinking about machine learning. But what I think is really needed for healthcare is one AI model per person, where we do what we always teach that we shouldn't do in machine learning, including me in my class. I always say we should never overfit, which is overfitting is where you make the model learn really well to what it's trained on, but then it fails to generalize to other people because it learned so well on what it was trained on. But actually, that could be a good thing if the use case of the model is to only be used on the person who it was trained on. Think about Face ID, where you give it a few examples, and now it can recognize your face in all sorts of situations. But it sucks at recognizing other people's faces, but it's really feasible with just a few labeled examples to recognize your face. And the key methodological innovation here is a relatively new area called self-supervised learning, where we have large data streams or per person, but they're unlabeled. So let me give a few examples. Let's Fitbit. So I'm wearing a Fitbit right now, or Apple Watch, or whatever you like. That's, in theory, continuously recording your data. And there's no labels associated with it, but you get your heart rate over many years. You get your ECG, hopefully over many years, accelerometer, movement patterns over many years. And that the baseline dynamics of those patterns are going to differ per person. So it's really infeasible to take Fitbit data and then predict stress for everyone, because there's so much variability in just how people use their Fitbit. And this is basically an impossible task, basically just as impossible as getting a really high performance AI model to look at someone's face and predict emotion with 99% accuracy. It's never going to happen because the way people express their faces is very different. But the way one person expresses anger is likely internally consistent, and probably in most cases is internally consistent. So if you get a few examples of them being angry or them being stressed, then, and you train the model on that, you can then predict in the future when they are angry or stressed or whatever, because you understand the basic dynamics. And the key here to make this work is we can train deep neural networks to make predictions about the incoming data itself, so that it learns about the dynamics of the underlying data. So for example, here we see, I forget what type of signal this is actually, Jonas, but do you know what type of signal that is? This one, this is like a canonical thing. It might be, I don't know, I think it's a cardiovascular signal, and it always looks like that. Not important. So what we can do is, if we have that over several months, we can mask out a segment of that signal and predict what was the missing segment for that person. And by doing that repeatedly, you generate a giant data set that's originally unlabeled, but becomes labeled through, creating these artificial labeled tasks. And if you can make those predictions, you have a neural network that learns to predict things about the person. And it basically understands the person. An analogy is these like ChatGPT-3. This is basically how that works too, where how does it do so well? Well, it's not like there's trillions of labels or 10 to the whatever, 500th power sentences that have labels to train ChatGPT. The way that's pre-trained is you take sentences without labels, you take out a word, you predict what was the missing word. And specifically there, you take two sentences and predict sentence 2 come after sentence 1, yes or no. You don't need labels for that. If you train a model in that way, your bottleneck is how much data can you get and how much processing power do you need? Because you just mine the entire internet and you can train your model in that way. And that's why ChatGPT does so well, by the way. So using that type of innovation for biosignals, I think, is very promising, where we can do the same thing. We predict things about the underlying structure of the biosignals. Oh, sorry, I'm just reading this. Is anyone having problems seeing? Oh, everyone's okay, got it. Okay, everyone can see the slides, great. So doing that same thing for biosignals and then fine tuning on really complicated tasks like stress, or in one case, I guess someone craving meth, which is a big problem in Hawaii. I'll get to applications in a bit. And so a lot of my focus now is in these different ways of training neural networks to predict things about the underlying signal, and then transfer learning onto what are traditionally complex tasks, but are now feasible due to this combination of self-supervised learning on a giant data set from that one person, and then fine-tuning on a few labels from that person. And so we have a few students who have worked on this. Tanvir has looked at this type of approach for this data set called WeSAD, which is the wearable stress and anxiety detection, something like that, data set, where he's basically forecasting, given one person's EDA signals, electrodermal activity, which is often a proxy for stress that some wearables measure. Can you predict what the next part of that person's signal is going to be based on what the previous portion was? Has gotten some interesting preliminary results. It's kind of hard to see, but the blue line represents a model trained with regular supervised learning on a deep neural network. The orange line represents one pre-trained with self-supervised learning, and the x-axis represents the number of data points used to fine-tune the model. So how many data points were actually used to train the stress detection. And we looked at this for 6 different questions. So predicting, I feel at ease, I feel nervous, I'm relaxed, I'm worried, I'm pleasant. Things that are pretty, like, you wouldn't expect AI to be able to predict that about people traditionally. But with this method, in a personalized way, it could work. And what we find is that with a few, when you have a few number of labels for a person, so the self-supervised pre-training does really well, because it's overfitting, which is usually bad, but in this context, it's good. So we have that in submission. I have other students who did the same type of method, and in this case, it was for emotion recognition, and from audio data, which is also a little subjective, and similar lines. So the blue line is the pre-trained model, and the orange line is the baseline model trained with regular methods. And what we find is that self-supervised learning gets better performance with just 15 labels than traditional deep learning methods do with thousands of labels. And so I think this is really promising for you on this path. Another area that I'm working on is benchmark data set development. So a lot of machine learning innovation happens by creating new data sets, releasing it into the machine learning community, and having them train machine learning models on those data sets. ImageNet's a great example of that. Some of these emotion recognition data sets are great examples. Kaggle has a bunch of these. And what tends to happen is if you curate a data set and release it to the public, all the AI people all around the world start using that data set and building AI models. So if you have a really challenging problem, why not crowdsource it to the machine learning community and let them solve it? A lot of what I'm interested in is curating these data sets, releasing it publicly, figuring out all the IRB and privacy issues that go along with that, and making it happen. So a few examples. Aditi has done this for Twitter data mining. So going back to autism, there is a hashtag called hashtag actually autistic that people put on Twitter. And typically you only use that hashtag if you have autism. And in fact, it's kind of like not good form to use that hashtag if you don't have autism. It looks really bad, actually. So what's nice about this is it serves as an automatic label for whether someone has autism or not, because of the social implications of using that hashtag. So what Aditi did was mine Twitter, and I think she has like millions of tweets that she mined, both of people who use this hashtag actually autistic, and then matched people who don't use it, some of them may have autism, but it's more representative of the average population using the law of large numbers. And we're looking at releasing this data set as a new NLP diagnostic data set for other people to look at. So those are methods that I'm really interested in. So in summary, multimodal machine learning, bare machine learning, personalized self-supervised machine learning, and data set curation in terms of data science machine learning methods. I want to pause there ask if there's any questions before I go into the application side of things. Hey, yeah, sure.
It's more about the machine learning and the data, or we use the machine learning. Do you ever like try to look at topological structure maybe that are associated with data or some geometry, you know, what space they might be high dimensional, but they want to know smaller dimensional space. Is that
Yeah,
might have, you know, I don't know.
yeah. It's definitely challenging because a lot of these data, especially the video data, is really high dimensional and complex. Typically, the way we reduce the dimension is not like PCA or anything like that, because it's unclear how that's going to reduce.
And that's the geometry, right?
Yeah.
So I'm thinking more topological data around this.
No, I don't. So the approach I tend to take is much more domain specific, where we extract features that are relevant to what we want to predict, and basically reduce the space, the complexity of the input space into an area that's much more feasible to machine learning. So for example, for autism videos, reduce it down to, you know, what's the fraction of frames where the child is looking at the frame. That's a nice low dimensional view. And features like that, little low dimensional vector, and then use like logistic regression on that.
What device did you use to collect DDA?
EDA?
Yeah.
Oh, so all this was on publicly available data sets.
Oh, okay.
I do hope to collect new data sets, and in the part 2 applications, I'll talk about some of the works that I'm in there. But yeah, I just looked at existing ones for now. It's my first year. Well, any other questions on chat? Okay. So one application I'm really interested in is detecting blood pressure spikes. This fits well with the personalized machine learning, specifically detecting blood pressure spikes from only Fitbit data and stress-related blood pressure spikes. So I've been talking to Dr. Kiabe at JABSOM, who, has anyone seen the HULA study from JABSOM? Okay, so there's this study from JABSOM that showed that hypertension was reduced by about 18 millimeters of mercury on average in this cohort of people who did this HULA intervention. And I think it's hard to know the causal reason, but likely a lot of that's due to stress. Like when you're chronically stressed, your blood pressure goes up, and that's not good. And so what I want to do is run a study where we have people wear Fitbits and wear a wearable blood pressure monitor and collect those data for a month, and then use those data to predict when is someone getting stress-induced blood pressure, which is different than hypertension. Hypertension is a diagnosis, blood pressure is an immediate symptom. And so this whole personalized self-supervised learning, I think, can work really well with this. And then once we have that AI, the next step is to then develop a digital intervention that will use that. And I'm thinking a simple breathing intervention. I actually tested this with myself and did like 10 deep breaths, and it went, you know, so it seems to work, at least on myself. But I think on, we'll try it on other people and see. But a lot of what I do is, okay, once we have the AI, what's the best way to create a digital intervention that people will actually want? And this is not designing things for people where it's like, here, I built this thing, now use it, but rather doing participatory design, bringing in people from the community and getting their feedback and really having them design it for us, and my lab being their customers. Like they tell us it would be really useful to have an app that would look like this. And then we built that for them. A little bit more involved than that.
I have a question on this. So
when you have participants wearing their monitors, do they also keep log of what they're doing, or do you just get the without internet?
So we get just a readout in addition to a corresponding mobile app that does something called an ecological momentary assessment study, which is a fancy way of saying every 30 minutes have a notification on their smartphone that asks them, like, how stressed are you, 1 to 5, how anxious are you, 1 to 5, and use that as additional.
Put in things like
No, I mean, I've been playing with that. There's existing models that can predict activities like walking or running just from these accelerometer and heart rate data. So I was hoping to leverage those, and but yeah, I mean, it might be just easier to ask them explicitly as well. Similar project on detecting meth craving and use. This is another area where, like, detecting if someone's craving meth, how is AI going to do that? It's going to severely overfit. That's basically impossible for AI. But with this whole personalized AI approach with self-supervised learning, it's potentially feasible. And so I've been talking with Dr. Guerrero and Dr. Bush from the Department of Psychiatry at Jackson, who put me in contact with Dr. Phillips, who's a researcher at Kaiser Permanente in Hawaii, who put me in contact with Heather Lusk, who is in charge of the Hawaii Health and Harm Reduction Center, which is a community-based organization for meth users, which is basically saying, if you're going to use meth, how do you do it safely, and don't police, but rather make sure people are safe when they're using drugs. And we're basically going to collect a similar type of data set as the blood pressure, but for meth. And oh, I should say, so how am I choosing these projects? So these are all based on needs in Hawaii. So Native Hawaiians have 4 times the adverse health outcomes from cardiovascular disease and hypertension than other groups, and are disproportionately affected by meth. So these are not just random projects. These are ones that I talked to people at Jackson for, and they're to let me know that these are the needs in Hawaii. Another area is social media data mining, which you kind of saw from the Twitter mining. So going back to Aditi's project, she, in addition to collecting that data set, she ran some machine learning on it to see, okay, can you predict whether someone basically has self-identified as having autism or not on Twitter based on all their tweets, stripping away all the autism related, obviously autism related words. So strip away the hashtags, strip away any autism, and just from their language, you predict autism. And it seems to do relative, reasonably 80-something% accuracy, which is interesting on a data set of millions, so it's big data. And then looking at explainable AI approaches to understand what specific words are making the classifier predict in a certain way or not. So on the left here, we see what the model predicted for a few example sentences, and on the right, it highlights in orange if that word was leading to a prediction of autism, and blue if it was in the random group. There's more to do here, but we're starting to look into understanding why these models make the predictions that they do using explainable AI. We've also collaborated with Dr. Pallav Pakral in the Cancer Center and his postdoc, Dr. Amin, on cigarette use. So similar social media data mining and basically predicting the probability of cigarette use from Twitter. This is a big area of interest by the NIH, where they want to do this public health surveillance on drug use specifically, and so we're starting to look into that. Really, this is Paulo's project, but Aditi has helped him out with that. So it's a nice collaboration. I started collaborating with Dr. Jerry Foster at the Hawaii Parkinson's Foundation on trying to detect Parkinson's and diagnose Parkinson's from how you press your keys and how you use your mouse. There's been a lot of previous studies in this field, and they've gotten pretty good results. So we're trying to look at it from a new angle based on a really easy to use game that the populations can play, but there's a lot of interesting user interface and design questions here with, okay, we're gamifying this, but these are older populations and we're asking them to play a video game. So how exactly we get engagement there? And so we're figuring all that out, but these are conversations that we're starting. An incoming student to UH next year, Ali, is working on personalized mood analysis. So he has built this really nice user interface app called STAND, which stands for Stress and Anxiety Detection, which basically pings people periodically to take a selfie of themselves. And then once they take the selfie, they label their mood. And then we're going to try out this whole personalized AI thing on that as well to see if you can detect depression or periodic depression using people's images. Kind of a moonshot project, but worth a shot. Classification of dementia using natural language processing. A joint effort with Ai Lin and RB Barone, where they're looking at the Dementia Bank, which is a big data set curated by Carnegie Mellon, which is basically text from a bunch of people with dementia and without dementia, and trying to build machine learning models that could diagnose, or at least distinguish dementia from not dementia from these data. I've been working with Dr. Shepherd at the AI PHI Institute on breast cancer, and we're starting to put together a few grants on fairness. I think I talked about this a little bit before, but fair AI on breast cancer data. We're collaborating with my old PI on some more autism-related projects where we're trying to predict autism using a combination of crowdsourcing and machine learning together. I think y'all have seen me give that talk many times, so more of that stuff. Collaborating with the Baylor College of Medicine and University of Houston, the other Northern Illinois University, on pediatric sleep behavior analysis. So we're getting kids to basically logging their smartphone use right before bed and then measuring how that affects sleep patterns. So this is a whole area of research called mobile sensing that one of my PhD students, Chris Slade, is looking into, where we can use our digital devices, our Fitbits and our smartphone devices to understand and quantify our general states of being. Interested in machine learning on big NIH data sets. So the NIH has released this All of Us research program, which is a data set of, they're aiming to get 1 million people collected. Right now they are only 300,000 and counting, but it's they're collecting biological data, so genomics, together with Fitbit data on behavior, together with electronic health record data on a really diverse population of people from around the United States, and as well as a bunch of health outcomes, cancer outcomes, diabetes outcomes, mental health outcomes, COVID outcomes, et cetera, mortality. And so And then there's been very few projects that have utilized this data set. So it's just kind of out there and waiting for researchers to do stuff with it, which is kind of surprising that this exists and people aren't using it yet. So if anyone's interested in looking at this, let's talk. But there's also Hawaii specific data sets that I'm looking at, the multi-ethnic cohort study. This is a data set of blood biomarkers and also genomics from a diverse group of people in Hawaii and California, together with the HIP EMR data set, which is mammography data collected in Hawaii and other Pacific islands, which is also collected from a diverse population of people. And this is a great these are great data sets, looked in particular at the FAIR machine learning projects, among others. So sorry, that was, an hour of all these different types of projects that you could work on. And there's many opportunities to work with me. Definitely an ML for healthcare. So if you want to do personalized, self-supervised AI, many projects there. FAIR AI, many projects there. Multimodal AI, many projects there. But beyond like the traditional data science and machine learning, I'm looking for people who have skills developing websites or mobile applications or wearable applications to curate these data sets and to create digital interventions that will actually help people with the AI that we develop. So, I mean, a lot of the AI will help people by providing good diagnostics, but a lot of the AI will also help people by being incorporated into digital interventions that are adaptive to the user. And not all of this work has to be quantitative either. I think there's a lot of work for students to conduct interviews and co-design studies with the population, community engagement, to learn what we should actually be building. We don't want to just build things in a vacuum and be like, here you go. We want to figure out what people need and create things accordingly. So yeah, that is all I have to say. Thank you for listening to all that, and I'll take any questions. So we have a question in the chat. Could there be quick healthcare wins for wearables? I think so. I think wearables are advancing really quickly in the sensors that they have and the openness of the APIs. So they have all these sensors, people are wearing them. Now they're becoming waterproof, which is great. Really long battery life. My Fitbit tends to last for an entire week before I need to charge it. And the APIs are pretty open. They've also figured out the security issues along with it. So I think there's a lot of opportunities to innovate there and to help people who already have consumer wearable devices or can get access to it if they can't afford it through health insurance or another means like that. But there's a lot of questions that need to be answered too, and with respect to data privacy. I didn't talk much about data privacy, but I think it would be awesome to have a student who's just focused on figuring out all these data privacy and data governance issues, which need to be figured out in order for these solutions to be put in the real world. And then, yeah, we have a comment, possible support for extending the internet to everyone, save healthcare costs. Yeah, so in the US, there's a lot of internet access, and internet access is growing globally, but it's still not universal. I think it's one of those things where hopefully, and maybe some correct me if I'm wrong, in 20 or 30 years, everyone will possibly likely have internet access. That's how it looks like it's going, but maybe I'm wrong. Any other questions?
Maybe a question. So I was recently at this workshop about common sense frameworks and building data sets such that we can develop models in a streamlined way. And one of them was about sensitive information for healthcare applications. I was wondering, instead of having to publish the data set that has sensitive information, have you seen frameworks in which the sensitive information is behind the wall and you just upload the model and then that loss is generated for you so that you can do that iteration?
Yeah, there's this whole area of research called federated learning, where you can train machine learning models locally and then just update their weights to a central server. Actually, my human-centered AI class, I talked about this extensively. But basically, you could average the weights of each of those local models. And so the weights of the models are not sensitive information. I mean, there's ways you can hack it, but in general, they're not sensitive information, just weights of the neural networks that have been learned. And so if you upload that to a server and aggregate that, you essentially have a general purpose model that can work for a lot of different people trained on all those different sites, but where the people from those individual sites don't have to actually share their data. You get that global model. That's something that I haven't looked into that much, but a lot of people in healthcare especially have been looking at that paradigm. I think it's a very interesting area.
Is a lot of analytics and data science and ML type stuff, is that kind of finding its way into like clinical medicine a lot recently? Because I read that it's maybe a little bit of a slow adaptation, but I mean, this stuff's like super cool and obviously has a lot of good to do. Is it kind of like penetrating its way into like clinical applications at the moment?
Yeah, it is. So my wife actually works at Kaiser Permanente, and she's involved with a lot of the discussions about the policy of the different hospital management. And sometimes I hear about, wait, this is being recorded, never mind. Basically, they discuss AI implementation within Kaiser, and a lot of like you can imagine with EHRs. Sorry, I won't say Kaiser specifically, within unnamed health companies. We blur this part out of the video. Anyways, I don't want to get her in trouble, but there's yeah, it is being used. I hear about it a lot.
Doctor, can you hear
Yes.
me? Okay. Hello. First of all, a couple of thanks for your marvelous presentation. And I wanted to know about the supposed to personalized medicine, personalized machine learning approach, how you collected enough data to train your model.
Yeah, so with the existing data sets that we've been exploring, we simulate it. So the data set might have 4,000 labels per person, like wearables, and we simulate what would happen if we only had 10 and see what's the performance. What would have happened if we only had 20, simulate that performance, and like bootstrap and take the standard deviation to be confident. But when we're collecting data, and in the studies that I've put in proposals for, what we're trying to do, what we only need is a really small data set, because it's not your traditional case cohort study. This is several independent N=1 studies, where you have one study where the whole training and validation test set comes from one person. And then you have another independent training validation test data set from another person. And you have thousands of labels within those, and many more, and hundreds of thousands of artificially generated labels via self-supervised learning within each of those single personalized data sets. And so, yeah, it's really about running a longitudinal user study, have people go home, wear a Fitbit for a month, and label their whatever health outcome we're interested in, and then and going off of there. But it is kind of a unique paradigm for doing machine learning, because traditionally in machine learning, you need a lot of data to build a general purpose model. And in this case, we need a lot of unlabeled data, but that could come from one person because it's unlabeled. We just need a few labels. Great questions. Any other questions? So this is all like, I guess I'll leave. Oh, yeah.
Just a quick comment. Thank you very much. This is super interesting, and I think we need to learn a little more what you do because it overlaps so much with what we do, but more on the data collection side. So we have 40 leads, and the newest one is sample set, whatever it is, 7-degree channels at 100,000 hertz. We do sleep activity and other things for sleep. What else we do? The FRI and OPM, lots of data. If you need anyone to collect data for any kind of project, let us know.
Yeah, we should definitely collaborate and yeah, thanks so much.
I have a question about that, because like during COVID, we did a lot and we were lacking actually some data that we have been to make a more accurate model and we identify the data. So is this in the description, like identifying type of data that maybe are not connected or are not accessible, that then you could guide the people doing the data protocol to see those are the data that would be key so that you have an extremely machine learning at the end of the type.
Yeah, it's that right now it's a much simpler approach of let's see what we can get, and the more the merrier by that. And prototyping with some of these small but publicly available data sets to get preliminary data to say, okay, well, you have all these modalities, look how much better it does, and that gives evidence, or at least provides supporting evidence to now run a larger scale data
Yeah.
collection.
No, I agree, but I'm just trying to see sometimes it's disconnected, the two words are disconnected.
Yeah.
And then, you know, we work with the available data, but maybe some data that could be connected or not connected because they don't know that it would be critical to the people who will be practicing or that. So
Yeah, this would be perfect.
Yeah, exactly. I like to see that.
Yeah, this has been great. Well, I guess I'll leave you with a lot of these are, you know, haven't been tried before, so maybe like 25% of it's going to work. But I think that's what's exciting about research is that, you know, we're not trying to build a company here. We're trying to make discoveries. And so I think it's worth trying out these creative ideas, and some of it's going to work, some of it won't, and that's okay. Well, thanks so much. Have a great weekend. And that's all I have.